Welcome to lesson 24. This is the last lesson. This is it. Congratulations that you got this far. It's been strong. Julie and I are going to split this lesson. So let's get going on this. So we have a linear function here, and it has a constant something. What? It doesn't have a constant. It has a constant rate, which is equivalent to its slope, or m. Just study those. An exponential function has a constant percent increase or decrease, which is the same as 1 plus r, aka the growth factor, or just the growth increase or decrease. The percentage growth increase or decrease, which is also called the factor. Now this should be familiar from you who had to take algebra. So a rate of change, a slope, is defined mathematically as the difference in the output divided by the difference in the input. And it's constant. That's key. A percent change, which we're going to need, is calculated by the difference divided by the starting value times 100, or the new value minus the original value, which is really just the difference, right? Divided by the original times 100. So we'll explore this. Okay, so we're going to take this table of values over here. Column A and column B. First column is input, second column is output. And we're going to find the rate of change and the percent change. And I'll go slow on this first one. So the rate of change, here's the formula. And so I'm going to take the second value minus the first value, or 1.015 E5, and subtract 1.082 E5. I'm going to put that in parentheses because it's in the numerator, and I have a separate denominator, and the denominator is just going to be 1 minus 0. It doesn't always have to be sequential. If this number, for instance, was a 4, it would be 4 minus 0. But it's not. It's a 1. So now maybe the question you have is, what is E5 mean? What does E4 mean? And I'm going to explain that and then come back to this. Okay, I'm just going to explain what this E5 means. And here's some examples I'm going to use. E2, E3, E7, E negative 3. This is just shorthand on your calculator or in Excel. Sometimes you'll see it like this, sometimes you'll see it like this. Depends on your calculator or your spreadsheet. It just simply is shorthand. E2 means multiply the number by 10 raised to the second power. E3 means multiply the number by 10 raised to the third power. E7 means multiply the number by 10 raised to the seventh power. And E negative 3 means multiply the number by 10 raised to the negative 3 power. Multiplying by 10 to the second is the same thing as multiplying by 100. Multiplying by 10 to the third is the same thing as multiplying by 1 followed by 3 zeros. Multiplying by 10 to the seventh is the same thing as multiplying 1 followed by 7 zeros. And multiplying by 10 to the negative 3 is the same thing as multiplying by the inverse, or 1 over 1,000. So let's go over here. So this is the one number that we have on our other sheet. So we would put this on our calculator, 1.085 times 10 raised to the 5th power. So now there's a couple ways. Different calculators have a little bit different setup. Most calculators, you can put it in like this, 1.085 times 10 with an upside down caret, that's called a caret, 5. And we used this before in Excel, and we used this before in our calculators. So this is the same thing as, I'm going to find what number this actually is. Multiplying by 5 tens would be the same as moving the decimal place 5 places. 1, 2, 3, followed by 2 zeros. So this number, 1.085 times 10 to the 5th power, is actually 108,500. So move the decimal 1, 2, 3, and 2 more places. So I hope that makes it clear what you're doing, what that E means. Okay, so this is the problem here I'm going to do, which is the first rate of change. I'm going to do it on the emulator, so I'm going to switch to the emulator. Okay, so I left you to do this one problem. Most calculators are similar to this, though most of them will have this caret over here, and most of them will look similar. So we're going to go 1.015 times 10 raised to the 5th power, come down off there, minus 1.082 and that's going to again be times 10 raised to the 5th power. And I'm going to get an answer here because I didn't put it in parentheses. So I got a negative 6,700. And what I'm going to do is hit the second key and the answer. So it brings the answer down. So that's negative 6,700. And then I have divided by 2 minus 1, which I can actually do in my head, believe it or not. And I'm getting negative 6,700. So that is our rate of change. Okay, I'm back. Perhaps for the last time. Anyhow, you might have a calculator that has a y, it doesn't have this caret. Instead, it has a y to the x key. And I'm just going to show you how to use that. Again, this is 1.015 times 10 raised to the 5th power. So this is how you can put it in your calculator when you have that y to the x key there. 1.015 times 10, and then you hit the y to the x key, and you put the 5 in. It's the same thing as raising to the power of 5. But use the y to the x key. So you punch in the 10, then you hit the y to the x key, and then you punch in a 5. So our first rate of change was negative 6,700. Let's do one more. So it's going to be y2, which is 9.48 times 10 to the fourth minus 1.015 times 10 to the fifth. Put that all in parentheses. That's y2 minus y1 right over here, divided by x2 minus x1, which in this case is going to be 2 minus 1, which even I can do that one. So these are going up sequentially, so the denominator is always going to be 1. So now why don't you try to put that in your calculator and I'll put up the answer. And if you did it like I did it, I got negative 6,700. Now why don't you try the last three and I'll put them up. But make sure you know how to do this on your calculator. And I did the rest of them here. You can see what I did. Here, here, and here. I did y2 minus y1 over x2 minus x1. Where's my denominator? Well, it's always going to be 1, right? Hopefully you know dividing by 1 is not going to change the answer. And so I got negative 6,700 for all of them. So that's the end of rate of change. Now I'm just going to do one of these and then put the answers in. But you want to try them. So the percent change is the new minus original, which is going to be, the new is going to be 1.015 e to the fifth. That's the new minus the original is 1.082 e to the fifth divided by the original, which we started with 1.082 e to the fifth. And so you want to put this in parentheses. If you don't put it in parentheses, if you just put it in your calculator, it's going to divide 1.082 by 1.082, and you're going to get 1.015 times 10 to the fifth minus 1. So that's why these parentheses are really important. So why don't you try putting that in your calculator? And when I put this in, I got negative 6.19%, or a decrease of 6.19%. And that's for the first one. Now I'm going to erase these here. And ask you a question. Now I'm going to do the next one, which is going to be 9.48 e to the fourth in parentheses minus 1.015 times e times 10 to the fifth. So that's the new right here, divided by the original right here, minus the original, divided by the original. 1.015 times 10 to the fifth. Put this in parentheses. Think about this. You notice what I'm going to get here? Every time I subtract the new from the original, what am I going to get? If you guess 6,700, you're on the money. But take your time and let's just get this one. And I'm getting negative 6.6%. So I'll put that here, negative 6.6%. So let's do these next three really quick. I'm going to have 8.81 e to the fourth minus 9.48 e to the fourth. That's going to give me a negative 6,700. I'm going to divide that by 9.48 e to the fourth. 9.48 times 10 to the fourth. You want to put that in your calculator. And then you're going to get another negative 6,700. And this time you're going to divide it by 8.81 e to the fourth, which is times 10 to the fourth. And then the next one is going to be a negative 6,700 divided by 8.14. 8.14 times 10 to the fourth. And finally, it's going to be again negative 6,700 divided by 7.47 times 10 to the fourth. Now I'm going to go up and just put the answers in here. But what do you think is going to be happening to these? Is it going to get higher than 6? Is it going to go up or down? The percentage, is it going to decrease by more? Stay about the same? And the answer is going to decrease by more, because look what I'm doing to the denominator is getting smaller and smaller and smaller, and the numerator is staying the same. So if the numerator stays the same and the denominator gets smaller and smaller, the number is going to get larger and larger. So try putting those in. I should actually play some music while you work it out. So here are my answers, and the numbers are actually getting smaller and smaller. The absolute value is getting larger and larger, but it's decreasing by a greater number each time. And actually did this one, but is that actually correct? Because I don't even have a number here or a number here. And the answer is, yeah, that's correct, because it's always going to be 6,700, because this is a linear function. It's the definition of a linear function. The rate of change is constant. The percent change is not constant. So this is a linear function. So let's create an equation. How would I create an equation? Well, all linear equations are of this generic form. And I have the slope. That is the rate of change. Times the input plus the starting value. What's the starting value? The starting value is right here. It's when the input is 0. It's the initial value. So that's going to be plus 1.082. I'm just going to stay with the e to the 5 so I don't run out of space. So that is that. The last thing we're going to do here is determine the output when the input is 10. So we're going to determine the output when the input is 10. So 10 goes in here. So I'm going to have the output equals negative 6,700 times the input plus 1.082 E5. or times 10 to the 5th. Hit pause, try putting that in your calculator, and I'll put the answer down. And I'm getting 41,200. So this is another similar problem. We have our inputs over here. Here's our inputs. Here's our outputs. We want to look at the rate of change and the percent change. So the rate of change is the change in the outputs divided by the change in the inputs. So for this one here, right here, it's going to be 81.2 minus 70 divided by 1 minus 0. And again, these are all sequential, so the denominator is always going to be 1. So this is going to be 11.2 do one more. It's going to be 94.19 minus 81.2. And for this one, I'm getting 12.99. Why don't you go ahead and put it on pause, work on these so you know how to do this. And then I'll put the answers up. And 5, 4, 3, 2, 1. So you can check your answers against the ones I just put up here. See if they match. Now let's just do the percent change. Recall again that the percent change is the new minus the original, divided by the original, multiply it by 100. So we're going to take the new, which is 81.2, subtract the original, which is 70, and divide it by the original, which is 70, and multiply that by 100. And let's just do the second one. It's going to be 94.19 minus 81.2 divided by the original, which in this case is 81.2, times 100 to make it a percentage. Why don't you put that in your calculator and give it a try. So if you got what I got, it's 16% here, 16% here. Try these three on your own, and I'll put the answers in. And you should have got 16%, 16%, and 16%. Does the table of values represent a linear or exponential model? And the answer is exponential. Why? Because the percent change is the constant factor here. The rate of change is increasing all the time. So that's exponential. Is it growth or decay? Well, it's growth because it is greater than, it's positive, it's 16%. which is greater than 0%. Being negative 16%, that would be exponential decay, which it's not. Yeah, I would suggest you put this on pause and take a good look at it. We're basically going to be looking at the common form, and this is the continuous form. This is financial model. It is so similar to the common form. It's very similar. 1 plus R is B. And A, which is the starting value, it's just they call the starting value here P sub 0. That's the initial values, starting value, A and P sub 0. B and E to the K and 1 plus R are the growth or decay factors. Now they work a little bit differently. B is pretty simple, okay? This is really simple. If we're going to increase something by 10%, as an example, you would just take 1 plus 10 over 100, put that in your calculator, and you're going to get 1.1. That is B. If you're going to increase by 10%. If you're going to decrease by 10%, that would be 1 minus the rate, 10 over 100. And you would get the factor of 0.9. That would be B. This works a little bit differently, E to the K. First of all, E is Euler's number, which is an irrational number, which means it goes on forever. It's about 2.71. You can check it on your calculator. And K is the continuous form of the rate. So if you're going to increase this by 10%, it would be E raised to the 0.10 times X, which is the number of times you're repeating that. And if you're going to decrease it by 10%, you would then use E to the negative 0.10 times X. It's a little bit of an explanation between the common form and the continuous form of the exponential function. So we're going to look at the following population estimates for Anchorage, Alaska from 2000 to 2010. Now we're not going to use 2000. It just doesn't work out. It makes a complete mess of things. So that's the year we're starting with. We're going to call, that should be 2000, not 2010. Let the year 2000 be year 0. And that's the population. And then here's 2001, etc. We're looking at the rate of change, which is y2 minus y1, right? Over x2 minus x1, and you can see that the rate of change is increasing. So it doesn't look very linear. But the percent change is constant at 12%. So this is an exponential function. Now we're going to write it out of the form y equals a times b to the x and explain what it means. Well, that is the output, which is the population, equals A, which is the initial value, which is right here. That's the initial value, because that's what we called the starting point. We made that decision. So that's 260,210. and 83 times the growth factor. B is the growth factor. Now, B is not 12%. 12% means 12 out of 100. If you take a number, I don't care what number you take, any positive number, and multiply it by 12 out of 100, you're not going to increase it by 12%. You're going to decrease it. You have to multiply a number by greater than 1 if you're going to increase it. B then is 1 plus R. It's the factor, which is 1 plus 0.12. Or if you like it better this way, it's 1 plus 12 out of 100. Which if you put in your calculator, you're going to get 1.12. That is B. That is the growth factor. Put that right here, 1.12 times the number, raised to the number of years since 2000. If this trend continues, what will be the population of Anchorage, Alaska in 2020? You're not going to put 2020 in for the input T. What are you going to put in for the input T? And if you answered and that should be a 3 here. If you answered 20 raised to the 20th power, you'd be correct. Put that in your calculator. And for this one, the output, which is the population, is equal to the initial value times the growth factor raised to the what power? And if you said 30, you would be correct. Well, try putting those in your calculator, and I will put down the answers here. Population in 2020, if it continues to grow at 12%, will be the population in 2030. If it continues to grow at 12% per year, it will be and so there's our answers right here. And it also kind of shows the power of exponential, because in the 10 years from 2020 to 2030, just growing at 12% per year, it more than doubled. So we're going to look at number 5 here, and then I'm going to hand it all to Julie. That's why I got my new hat. So, whatever. So, number 5 is the following illustrates the difference between compounding with the common form. And here is the common form, y equals ab to the x. And compounding yearly with the continuous form, continuous compounding. Now recall from chapter 1, remember we did compounding every quarter or compounding every month. You can even compound every day. Continuous compounding means you're compounding infinite amount of times per cycle. Now there's definitely a difference. If you're compounding continuously, you're going to wind up, if you put $5,000 in the bank to start, you're going to wind up with more money than if you compound it yearly. But let's get the equations down. So we're investing $5,000 at an APR of 4%, compound it yearly, which is here, and compounding continuously, which is here. So we start out, we're going to say the amount of money that I'm going to have, or Y, is going to equal my initial value, A, which is $5,000, times my growth factor, not 4%, but 1 plus R. The growth factor is 1 plus R, or 1 minus R. In this case, it's 1 plus. So it's 1 plus 4 over 100, which if you put it in your calculator, you get 1.04. That's the factor. Obviously, the factor has to be more than 1, and that's raised to the number of years. Now, for the continuous form, it's going to be the money that you have in the bank after a certain amount of time is equal to A, which is the initial starting value, 5,000, times Euler's number, which is on your calculator, it's a little e, raised to the k, which in this case is, here's where you get 0.04, because 0.04 is 4 over 100, times the number of periods. Now we worked out here every year what you're going to have for each one of these different forms. Notice that in this form, after 5 years, you've got $6,083.26, compounding yearly, compounding infinitely or continuously. After 5 years, you'll have $6,107.01. So we're going to find out. Well, we just did determine the equations. And we want to determine how much you will have in the bank after 30 years with each different form. So let's do first the yearly compounding. I'm going to have in the bank my output, because it's the second column, it's the output column here, right? That's the output, is going to equal my initial value times my growth factor raised to the 30th power. If it'll stay there. And we'll figure out what that is in a second. And for my second one, it's going to be my output, again, the amount of money I have in the bank is going to equal my initial value times Euler's number, which is about 2.71, raised to the percent that you're compounding continuously, 0.04. Notice this is different. This is different because this is 2.71 times the number of years, which is 30. So let's put this in our calculator and get a number for that. You can try that one. This one I'll pull up the monitor, and so we can show you where Euler's number is. So in this model, I'm getting $16,216.99 compounding yearly. Now I'm going to switch over to the emulator and put this in the emulator. Okay, so now we're going to do the continuous form, which starts out the initial value, $5,000, times Euler's number. Euler's number is right here, the little e, below the pi, but it's in blue. So you hit the second, I bring you to this blue level, and there's your e. Then it's going to be raised to the 0.04 times 30 years. And there's our amount. So for the continuous form down here, put it in red, continuous form down here, when we put it in the calculator, we got $16,600.58. importantly, notice that this is, hundreds of dollars more than this. So that compounding continuously, you're going to get more money. Okay, that's it for 5. I'm giving it over to Julie. Julie, take it away.
All right, great job. Thanks, Peter. Now, is what we want to take a look at is example 6. What we want to note about it is that any spreadsheet that we use mostly is going to use the continuous form. What that means is that I can have Microsoft Excel come up with these equations for me, and they're going to use the continuous form, which remember is this form right here, the one with the E in it, Euler's number. Because of that, it's very useful to be able to convert between this form and this form. All right, when we do financial examples, a lot of times we see this form over here, so we have it there just for information. Now the following equation is the same equation shown in 3 different forms. Notice how the orange piece, which represents the initial value. And now I know some of you guys have a black and white copy, so the orange piece is going to be this 100. It represents the initial value in each one of them. It's the same in all 3 forms of the equation. Also notice how the blue piece, which represents the growth decay factor, is the same in all 3. The growth decay factor is going to be the 1.35, that's the blue piece. This e to the 0.3001 is the blue piece, and this 1 plus 0.35. And if you look at that, you have an initial value times the growth or decay factor raised to some power. Initial value times the growth or decay factor raised to some power. The initial value times the growth or decay factor raised to some power. Now please be careful because order of operations when we solve these tells us we have to do this entire piece raised to the power before you multiply by that initial value. Why is that? Pemdas. Remember, parentheses come first, then exponents, and then you multiply and divide. So you want to do this raised to the exponent before you ever multiply by that 100. All right. What is e to the 0.3001? Now you guys might be pretty good at your calculator. If I look here, I don't see an e button, okay? So I'm going to go ahead and I'm going to view my scientific calculator. And as what I see is I still don't see an e button. I see a pi button, okay? But as you know, e is 2.71828 blah blah blah, right? So I'm just going to estimate because I don't have an e button here. I'm going to go 2.71. and I'm going to raise it to the power of 0.3001. So to raise to the power, I use this x to the y key. So I'm looking for the x to the y key, and I'm going to type in 0.3001, and I'm going to press enter. And I'm going to get 1.349 approximately. What is my initial value? Well, we know my initial value is always the orange piece. It's that starting value, so my initial value is 100. Does this equation represent growth or decay, and what is the growth decay factor? Well, because my number is above 1, it's representing a growth. And my growth or decay factor is the 1 plus or minus r. So you can see over here we have 1 plus 0.35. This 1.35 is my growth factor, which is what? The same as e to the 0.3001, which is 1.349, which is approximately what? 1.35. So my growth decay factor is just 1.35. How would I know if an equation represents decay instead of growth? Well, it's going to be less than 1 instead of greater than 1. So this is 1.35. If you think about 100 and you take 100 and multiply it by 1.35, you're going to get what? Something bigger than 100. If I took 100 and multiplied it by something less than 1, let's say 0.65, I'm going to get a decay. It went from 100 to 65. So therefore, how do I know if an equation represents decay instead of growth? Well, it's going to be less than 1 instead of more than 1. Now, what is the continuous rate for these examples? Well, if I go up here and I look at the continuous rate, the continuous form is the one with the e in it because it compounds continuously. My continuous rate is going to be this rate up here, 0.3001. Now, I want to turn that into a percentage, so that's going to be what? 30.01%. And my associated rate is the rate at which this is growing, so that's going to be what? 1 plus 0.35, as shown in this example over here also, that's going to be what? 35%. So if you're confused on how I got the continuous rate, it was 30%. It's the k value in y equals e to the kx. So the k value is 0.3001. And the 35%, the associated rate per unit, is the r value in 1 plus or minus r, which is going to be what? 0.35. So it's 35%. If you're only given this form, it's very easy. You just subtract the 1, right? And you're left with 35%, 0.35. All right, so hopefully you guys enjoyed question number 6. Go ahead and take it away, Peter.
So for each of the next 2 examples, we want to identify the starting value, the continuous rate, the growth or decay factor with the associated rate, and convert the given equation from the Excel form, which is this form here, it's the form Excel gives you, or any spreadsheet, to the common form y equals abx, and then use that. So the starting value should be obvious. There it is. It's 1,200. $1,200 because we're dealing with money. The continuous rate is right here. It's 0.1655 over 1. Multiply both the numerator and denominator by 100 to get a rate, and we get 16.55%. Now, we already have down here, we can already start our formula because we're switching over to this one. The starting value is exactly the same. And we want to find out what factor we're going to multiply by. Well, look over here. This is being multiplied. $1,200 is being multiplied by E raised to the 0.1655. Now, if we put that in our calculator, we're going to get 0.18. And 1 plus R is going to be 1 plus 18 over 100, or 1.18. So that's our decay. Our growth rate is 18% when we're using the yearly form. Now this equation that we just made here is identical to this equation given in Excel. What we're doing is making the conversion. And if you think about it, you're going to need a little bit more of a percentage here to compensate for the fact that this is the continuous form of the equation. So how much will be in the fund after 20 years? Well, we're going to say the amount in the fund after 20 years is our initial value times 1.18 raised to the 20th power. Put it on pause. 3, 2, 1. So it's going to be almost $33,000. There's our answer, which you should have gotten here. Make sure you practice with this. Find E on your calculator and raise it to that, and make sure you can get 18%. Because what we're doing here is we're converting this equation to this form, the common form. So this is part 2 of that. We just want to look at what we have here. We have a chemical spill, and this is the days since the spill. And this is the number of contaminants in parts per billion. So there's 20 parts per billion in this spill. That's the initial value, right? 20 parts per billion. So we can already put that in the equation we want to develop, which is the common form. The continuous rate is negative 22.3, negative 0.223 over 1, which is a negative 22.3%. Now our growth or decay factor, or 1 plus R, is simply what is 20 being multiplied by? In other words, what is this number here? X is just the number of days. So what is 20 actually being multiplied by? It is being multiplied by E raised to the negative 0.23223. Let me redo that. Negative 0.223. And let's put that in our calculator and see if we can get a match. And if you got 0.8, you would be correct. If you think about it, that's about a decrease of 20%. 1 minus 20 over 100 is going to be 0.8. So it's an increase of about 20% when you change forms. So there is the form of the equation, which is the same now as this one. So this would be 0.8 because E raised to the negative 0.223 is 0.8. Confirm that on your calculator. So the decay rate is going to be 20%, right? It's decaying by 20%. So we're going to say what's the parts per billion going to be after 38 days? So the parts per billion, which is the output right over here, is going to be equal to the beginning initial value times 0.8 raised to the 38th, because those are the days. Hit pause, see if make sure you can get that. And I'm getting 0.016 parts per billion. Number 9 is actually pretty cool, but Julie's got to come do it, which I think is really cool. Take it away, Julie.
All right, thank you, Peter. Let's go ahead and take a look at what we have going on here. Chuck bought a tractor for $30,000 in May of 2000. The value of this tractor, even after the first few years, is shown in the table below. Let's go ahead and determine if the tractor is depreciating linearly or exponentially. All right, so in order to do this, we have to go back a little bit and think about what is the difference between a linear depreciation and an exponential depreciation. So if I go back a few pages, and I go back to this page where we discussed linear versus exponential. It's in the last lesson, the last page of the last lesson. Remember, if the total or absolute change is constant, so if the total or absolute change was the same, then we had what? A linear function. If the percent change was the same, as in this example below, then we have a what? Exponential function. So what we're going to do is we're going to create 2 extra columns here so that we can calculate the absolute change and the percent change. If the absolute change is the same, we're going to have what? A linear function. And if the percent change is the same, then we'll have an exponential function. Before we do this though, let's go ahead and change our data. Let's change it so it's just a little bit easier. We're going to change this $24,003. We're just going to change that to $24,000. So if your version of the workbook hasn't been updated yet, go ahead and change that to 24,000. It may already be updated. Now let's go ahead and really quickly calculate the absolute change. Remember, you're not going to use this first one. You're going to calculate the absolute change by this one minus this one. That's what's going to go in that first box. So we're going to go ahead and do 24,000 minus 30,000, which should be negative 6,000. Now I'm going to do 19,200 minus 24,000, and I should get negative 4,800. Well, we can already tell that these aren't the same, so it's probably not going to be linear. Let's see what our percent changes come up to be. If they're the same, then it'll be exponential. How do I calculate the percent change? I do the new minus the old, and I divide it by the old. So let's go ahead and take 24,000 minus 30,000, which we already have here is negative 6,000. So we're going to start with 6,000, make it negative, and we're going to divide that change by what? By 30,000, the old value, and we're going to get negative 20%. Let's go ahead and calculate the next one. For the next one, we're going to take that 19,200, subtract the 24,000, which should give us what? That result already of negative 4,800. All right. Then we're going to take that value divided by the old value, which is 24,000. And we get negative 0.2, which is negative 20%. Awesome. So we can see that the percent change, it seems to have a pattern that the percent change is going to be what? The same all the way down, which makes this function follow what? The exponential model. So is this tractor depreciating linearly or exponentially? Well, we decided it was exponentially. Why? Because the percent change column was the same. Does this data have a constant total change or a constant percent change? Well, remember, another way of saying absolute is saying total change. And another way of saying percent change is relative change. Don't let all the words confuse you. So does this data have a constant total change or a constant percent change? Well, it has a constant percent change, and that was what? Negative 20%. Let's go ahead and fill in the remaining values of the tractor in the chart to the left. I can use Excel if I want to expedite this, but this really isn't hard. How do I do this? I start with $30,000, and I'm going to multiply that by my what? My 1 plus or minus R value. My R is negative 20%. So if I want to multiply by 1 minus R, I'm going to multiply by what? By 1 minus 0.2, which is 0.8. So I'm going to take that 30,000, I'm going to multiply it by 0.8, and I should be left with this 24,000 right here. Oh my, there it is. I'm going to take that 24,000 and I'm going to multiply by 0.8, and I should be left with 19,200. Oh, this is cool. I'm going to multiply by 0.8, and I'm going to be left with 15,360. I'm going to multiply by 0.8. I'm going to be left with 12,288. Why don't you go ahead and finish that? Let's go ahead and do letter D. Write an appropriate equation that will accurately determine the value of the tractor after X years. Well, I have quite a few different forms of this equation. Let's go back and pull our forms of the equation from a few pages ago. I have the what? The common form, the continuous form, and then this other form. Let's go ahead and write those down. All right, so I have all three forms of the equation written. Now, all of these right here, my A, and my P sub 0, these are all my initial values. My initial value is my starting value. My starting value is all the way up here. It's what? At year 0, I bought that tractor for $30,000. So my starting value is $30,000. Now we'll just start with the common form, $30,000. Now I'm going to multiply that by what? By whatever my B value is. What's my B value in this equation? Remember, the B value, the e to the k power, and the 1 plus R value is all my growth or decay factor. So my growth or decay factor is going to be what? It's going to be that same thing that we multiplied by all these things to get the next number. It's that 1 plus or minus R value. So my growth or decay factor is going to be what? 0.8. I need to raise that to what? The x power. So now I have 30,000 times 0.8 to the x. Now what a lot of students want to do is they want to take 30,000 and multiply it by 0.8 to make it look a little bit nicer. But why can I not do that? Why? Because of Pemdas. Remember, order of operations from back in the beginning of the semester. The first thing you handle is parentheses. The next thing you handle is exponents. After that, you can handle multiplication, division, and addition and subtraction. In this case, I have an exponent, so this piece is its own piece. So you have to do 0.8 to whatever that x value is going to be before you multiply by 30,000. Now remember what my x and my y values are. They're just what? Different points on the graph. For example, I've graphed this function for you. Let's take a look. So here's what the function looks like. It has a starting value of $30,000, and as the years go by on the x-axis, the value of the tractor goes down. All right. So I've made a table of values. Let's go ahead and get rid of me so that you can see this. I have a table of values here which matches the table of values that you should see on your paper. If I go ahead and put these points in, this first point is 0, 30,000. That means at 0 years, x is 0, my y value, my output, is going to be $30,000. If I go to 1 year, my input, x value of 1 year, is going to have an output of 24,000. I can continue through all of these values, and the x just represents a different year on the graph. So at 4 years, my tractor is going to be worth $12,000. I could extrapolate my data and look all the way up at 20 years, and in 20 years, my tractor is only going to be worth, $345. The input is the years, the output is the value of the tractor. So hopefully this makes a little bit of sense as to why we have an x value and why we have a y value. They just represent different years and different tractor values. All right, so in this equation we put 0.8 because 0.8 was what? Our growth or decay factor. And all that B stands for is what? Your growth and your decay factor. Now, let's see if we can come up with one of these other two equations. Y equals A times e to the kx. Well, e to the k is our growth factor. It's not just the k value. You have to do e to the k. So we need something that says e to the k equals 0.8. This is a bit challenging for us to solve in this class because we haven't discovered logarithms yet. If you've taken pre-calculus, you can solve this by the rule of logarithms or by taking the natural log of both sides. However, in this class, we're going to settle for Microsoft Excel to give us this equation. Before we go to Excel, though, let's try and create this third equation here, this one on the far right. My initial starting value is $30,000, and I'm going to multiply that by what? 1 plus R, or 1 minus R. In this case, we had what? A percent change of negative 20%. We said our decay factor was 0.8 because we took 1 and subtracted our rate of 20%. So really all this is it's 1 minus 0.2 to the t value, and t is going to represent time, and my y, or my p in this case, is going to represent the tractor value. So you should be able to come up with these equations giving a set of data. This one you should be able to get using Excel. So the equation that I got is y equals 30,000 times e to the negative 0.223x. And if I were to punch e to the negative 0.223 into my calculator, I would get 0.8, which is the same as that equation of y equals 30,000 times 0.8 to the x power that we got in the previous example. So hopefully this makes sense. And back to you, Peter.
Well, this is it. Number 10 is not there, and this is the last problem. One error here. That is not billions, it's US dollars in millions, which is 10 to the 6th, right? And same thing here, US dollars in millions, 10 to the 6th. You should know that, like 10 to the 3rd is thousands, 10 to the 6th is millions, 10 to the 9th is billions, 10 to the 12th is trillions. So we're going to look at Social Security expenditures, years since 1985. And these are the dollars spent in Social Security. The dots are the actual data. The dollars spent in Social Security in different years. Here's a linear model, and here is the exponential model. Notice in the real world, it's not exact. You're not going to get an exact, you're trying to get as close as you can. How do you know how close you are? The residual squared. A perfect fit is 1. a darn good fit can be 0.7. So this is a really good fit, 0.9583. And this is a really great fit, 0.9982. This is an excellent fit. You can see that the model or the equation is really closely following the data. Where here the model follows the data, but it kind of falls off here. It looks like it's starting to expand. The amount of money we spend on Social Security is starting to expand pretty rapidly, and it is because the retirement of the boomers. There's many millions of boomers retiring, and so the Social Security expenditures are tending to go more exponential as they are here. So what model is a better fit? The exponential. Use your model to extrapolate. That means predict outside the data, like somewhere up here. Predict outside here. Use your model, your equation, to predict somewhere out here what the total expenditures will be for Social Security in 2019. Well, let's just go ahead and use this formula. So I'm going to have the total expenditures equals 195,933 times E raised to the 0.0504, I believe I see. And what goes here? This is going to be the years since 1985. So we have 2019 minus 1985. And I'm getting 15 and 19, which is 34 years. So 34 goes up here. So try putting that in your calculator and see what you get. So if you put in your calculator, you should have got something like that. And remember, I changed this to millions here. So that's not really the dollars, that's the millions of dollars. So that's times 10 to the 6th power. So instead of moving it 6 decimals, watch this. I'm going to move it 3 back the other way. That's times 10 to the 6th, 10 to the 7th, 10 to the 8th, 10 to the 9th. It's 1,087 times 10 to the 9th. You might want to explore that a little bit. Because I know down here, this is what it says. How well did your model predict the actual expenditures of 1,044 billion? Which is times 10 to the 9th too. So now we can look at this and compare them. And I would say the model predicted it pretty well. And so that is a wrap for this class. And if you're old enough to have a glass of wine, have a glass of wine, because I'm gonna, and that's the end of the class. Except for you got one more dependency project to do. Well, it turns out we have a question 10 after all that I missed. But this is only going to be 30 seconds. It says r squared, which is the number here and the number here, is a statistical measure of how close the data are fitted to the regression line. In other words, the model line, the equation, How close does that equation actually fit the data, or that equation? If r squared values are between 0 and 1, that's the values. They can be anywhere between 0 and 1, with 1 being a perfect fit. And something like a 0.7 is darn good. So this one here, you can see the data is in blue and the line is the model for this, which is a linear equation, so is this one. And here's the data, the little blue dots, and then the line of best fit is sort of dotted there. So they're just asking which one better fits the data. Does this line better fit this data, or does this line better fit this data? And the answer is, at a 0.997, that is almost a perfect fit. And you can see it's almost a perfect fit because the line actually corresponds really well with the data. Over here, this is a pretty good fit. The data and the line are corresponding pretty well, but you got gaps here and gaps here. And so the answer is data set 1. And that, my friends, is a wrap.